So hello everybody. So I'm Christophe and I'm going to tell you about the works that we are developing in Université Paris-Saclay and which concerns the certification of quantum programs. So the basic idea is that quantum computers are going to arrive and to be available for programmation in a near future. And we want to know how to write programs for these computers that we know to be correct programs with regards to some specifications. So to do so, we need specification and verification mechanisms. We want them to be parameterized or to be able to tackle parameterized algorithm and in particular scaling variants. And we want them to be automated as far as possible. And so for this, we are developing Qbricks, which is a core building circuit language that comes with a circuit semantics, an high-level specification framework, and a proof of engine for the certification of quantum programs. And thanks to it, we could implement and certify the implementations of some emblematic quantum algorithms, such as the Shor order finding. So I will first tell you a bit about verification of quantum algorithms. Then we'll have a look at what to verify, what are the specifications for quantum algorithms. Then I will introduce briefly the higher order path sums reasoning. That is the main reasoning tool that we are using in Qbricks. And I will conclude this talk. So first, the present state of affairs in quantum computing is that we have a collection of quantum algorithms that have been developed and proposed in the literature. So here is the Shor order finding algorithm from the Nissan and Schwang book. So we have these algorithms. We now have a collection of quantum programming languages, such as Creeper, and these languages proceed by building sequences of quantum instructions, quantum computing instructions, so the so-called quantum circuits. And so our question is how to get sure that a circuit that is built by a quantum program which aims at implementing a given algorithm, whether this circuit is effectively a run of this algorithm. So this question is quite standard in computation, but it is a bit particular in the quantum case for several reasons. Maybe the first one is that maybe quantum programming is especially tricky and non-intuitive. And here I give this warning by Richard Feynman saying, if you care your intuition, don't trust your intuition, basically. This is the first thing. And maybe more concrete reasons. The first one is that there is no means to run a circuit and within the run to include some, let's say, tests for the value of a variable or so on, and then to restart the execution. This is not possible because of the destructive measurements. And third reason, the quantum computation is not deterministic. So what one would have to verify, what one has to verify is a statistical distribution over the executions of the circuit. So if he proceeds by test, he will have to run a set of tests that needs to be large enough to rebuild a statistical distribution, which is expensive and in particular time costly. So our conclusion on that is that a strategy of verification that would be based on testing is difficult to handle, not to say impossible. And so we propose a full verification because this brings solutions to the dead ends that we just saw. And in addition, it enables to verify unbounded state spaces and to provide once for all absolute guarantee of the correctness of a program. So this is what we are proposing with Qbricks. Now, let's go back to quantum algorithms themselves. So again, is as the example, the Shor order finding from the Nielsen and Schwang book. And just looking at the structure of the algorithm, it is made of two parts. First, there is a preamble that plays the role of a specification. And this specification preamble contains the data of the input parameters. So things as the size of the quantum register, the oracles, etc. It also contains a functional correctness specification, that is a specification of here the output of the algorithm with regards to the input, so specifying the input-output relation, and it contains at last a specification in terms of complexity, that is a runtime bound. So this is for the specification preamble. And now the algorithm also contains a procedure which is structured in 2 columns. On the right-hand side, we have a sequence of operations that are declared. And in parallel, on the left-hand side, we have a sequence of intermediate assertions, intermediate formal assertions, that are description of the state of the system and of its evolution along the performance of the operations that are declared on the right. So this can be interpreted very naturally as a contract for the one who will implement the algorithm. This is the way we interpret it. So for example, here there is a function create superposition that is declared. And what the algorithm says is that this function can be implemented in any way, provided that if we give it an input that satisfies the blue precondition from the first line, then the output of this function should be like described in the second line in red. And so we can write it explicitly, declaration of the function, its body, and explicitly within the code, the explicit mention of the precondition for the input and the postcondition for its output. So this kind of writing is annotative programming, and it's a very common tool for deductive verification. So our strategy is to use such a programming language. And so we embed our development of Qbricks in the Y3 environment. Now, the input of an algorithm are often integer parameters such as the size, etc., and also an oracle U. This oracle U is a subcircuit, and it is varying. We don't know explicitly what it is, what it does, but it is given with a specification in terms of its input and its output. And building a quantum circuit for an algorithm will consist in building around this oracle a larger circuit by composing with sequence, control, parallel, and so on, so as to extract some useful information from the oracle input. And this oracle is given with a specification, and the general form of these specifications is the following one. So if the input satisfies a given precondition, then outputting the oracle to this input should result in something that satisfies a postcondition. So here are a couple of examples. We can take the Grover example. So precondition, if the input is an element of the computational basis indexed by I, then outputting the oracle to this input will result in another element of the computational basis that is indexed by the function f, which is a parameter of the algorithm applied to the input I. So this general form, precondition on the input implies postcondition on the output. And this is extremely practical for reasoning about the composition of circuits, because if we have a circuit that leads from precondition P to Q and another one leading from Q to R, then composing them in sequence will lead from the precondition P to the condition R. So we can apply the cut. This is the way we want to reason about quantum programs, and for that we need a formalism for reasoning about inputs and outputs of parameterized quantum circuits. So let us look again at the Shor order finding algorithm, and just the left column, the formal specification of the quantum states, and just notice that they all have a kind of specific normal form with a scalar coefficients time a sum of terms that are defined by the elements of the computational basis. So this generic normal form has been formalized recently by Matthew Amy with the so-called pass-sum semantics. The basic idea is that for any quantum circuit and any input of the computational basis, applying this circuit to this input will result in a state having this specific form. And this specific form is a scalar determined by an integer parameter r in red and a sum of terms, sum bounded again by help of the red r. And in each of these terms, there is a complex scalar coefficient of modulus 1 given by this blue function and an element of the computational basis given by the green function. So basically, to completely characterize the action of a circuit over any input gates, we need three separated parameters: the red integer, the blue function, and the green function. And the interesting thing is that each of these parameters receives a recursive definition over the structure of the circuit. Okay, so pass-sum enable for any quantum circuit to identify a pass-sum that is correct for this circuit, but now quantum programs are often parameterized with size, with oracle, etc. And so we are talking not about circuit instances, but we are talking about parameterized circuits. So with these parameters indicated with this X. And to talk about them, we generalized the pass-sum framework to what we call higher order pass-sums that are pass-sums given with parameters. And so this is what we are using to reason about the quantum generalized circuits. So the first step is to identify for each elementary gate a pass-sum that is correct for this gate. So here, for example, is the rule for the Hadamard gate. We see that given a pass-sum H, if it satisfies three different conditions, one for the red integer, one for the blue function, and one for the green function, then this pass-sum is correct for the Hadamard gate. And so we did the same for each elementary gate, and also we introduced reasoning rules for the circuit combiners. So here is the example of the sequence combining. We are talking about HOPS, so with parameters. And basically, if we have three different HOPS, the first, the second, and the third, if the first HOPS is correct for a generalized circuit C1, and the second is correct for the circuit C2, then if, in addition, the third HOPS satisfies three different conditions defined by help of the elements in the first and the second HOPS, one condition for the red integer, one for the blue function, and one for the green function, then this third HOPS is correct for the sequencing of circuits C1 and C2. So we can define for each parameterized circuit an HOPS that is correct for it, and this enables to derive reasoning rules for reasoning about the output of a given circuit on quantum input. So there is a rule for the circuit application. I think I don't have time to present it. And we also have tools for reasoning about the probability of outputs of measurement on quantum circuits that are also derived from the HOPS framework. This comes with equational theories to identify equivalent HOPS and so on. And also we developed simplified rules that applied for certain specific fragments of the language. Like, for example, the one where the red integer has a special value 0. Okay, so this is basically the way we are reasoning in Qbricks. Thanks to it, we could implement several emblematic quantum algorithms. And here is just as an example, the specification for the Shor order finding implementation. This is given in an OR style. And I just want to have a short look at the post conditions that we prove. they are basically similar to the ones that we saw at the beginning of the presentation in the view of the Nielsen and Schwang manual. So there is a postcondition talking about the probability of getting a result after measurement that is useful for the computation. And there are specifications about the complexity of the circuit. So about the size, that is the number of gates, about the number of ancilla qubits that are used, and about the width of the quantum circuits, that is the number of quantum wires that we needed. Just a view on some data about the complexity of the implementation. We are just looking at the blue figures. So for the whole Shor order finding implementation, the length of the code, including the specifications and intermediary lemma, is about 1,200 lines of code long. At compilation, it generates a little bit more than 2,000 proof obligations, and 95% of them are automatically discharged by calling to SMT solvers, which is enabled by the Y3 embedding. And to finish the proof of the wasting proof obligations, I had to enter manually 456 interactive commands. Okay, so as a conclusion, we developed a circuit building language. We generalized the path-sum semantics with parameters that gives tools for reasoning about parameterized circuits that are natural, that are close to textbook. Looks like they look like the way algorithms are specified in textbook, and it is also very convenient for the automation of reasoning. We also have a dedicated specification language that lies on the HOPS, and a deduction system, HQHN, that I just introduced in this talk. We implemented the rule in the Y3 deductive verification web framework, and thanks to it, we could implement parameterized verified versions of several algorithms, such as Hoover, QPE, or the Shor order finding. And this brings an improvement with regards to the state of the art in terms of automation. Yeah, that's it. I thank you for your attention and looking if there are some questions.
All right, thanks for the talk. We quickly check the Slack channel. So maybe while questions are coming in, you were mentioning the table in the end, like this 565 or something about that manual commands, or 546. So can you link this somehow to time, like wall clock time? So how complex are they? Is it like clear what to do, or how long would it take you to do that?
To find the good 456 commands that enable to finish a proof, you mean?
Yes, exactly.
Yeah. It's I don't know. It's a bit long. It's a bit long. That is sure. No, actually, the main challenge in this story is to reduce this human proof effort that is needed for programming. I interpret this 456 as a clear progress when we look at the state of the art, but it is also a remaining challenge. Not to give a proper answer to your question, I don't know, maybe 10 hours to, yeah, but honestly, it doesn't mean anything. But yeah, it is on the way of reducing.
All right, thank you. Like another question we got from Ross is, so what would be the most interesting properties that you can specify for, and two, that you can feasibly prove using the system?
Yeah. Thank you for that. Up to now, the properties that I focused on are the functional correctness, so that the algorithm gives the expected result with a good probability, and the complexity. And so I focused on it, and I did it. I think for further improvements, it could go towards the evaluation of risk of error and the efficiency of error correction framework, I would say.
Right. One more question we have. Like, can you say anything about variational algorithms in context of this framework?
About variational algorithm, is it?
Yeah, exactly.
At the present state of affairs, I can just say that I'm interested in developing them in Qbricks. Actually, Qbricks at the present state of development talks about unitary operators, about pure quantum circuits. And there is no, for example, there is no measurement operation. We just reason outside the circuit about what would happen if we did the measurement. Then a natural extension of it would be to introduce this measurement and then some classical control structure. And with that, dealing with hybrid algorithms such as the variational could be possible, and it is also a target.
All right. Thank you very much. I think there are other questions and more discussion we can have on the Slack channel. And thanks again.
Okay. Okay, thank you.